So I appreciate the invite today to FNL Asia. This is the second time coming out for a presentation. It's always an honor. So what I'm going to talk about is fuel economy, especially with respect to our next generation dexos specification. The font is not quite the best here, so bear with me. In terms of what we're doing today, we just recently launched our second generation dexos specification. Primarily dexos1, dexos2 will be coming up within the next year. The main focus is around fuel economy. It also incorporates the robustness of our first generation dexos1, which if everyone recalls with dexos1, it takes basically an upper tier window of ILSAC GF5 and marries it up with ASEA requirements as well as a couple GM Opal tests. Increases performance and fuel economy, and I'll get into that in a little bit. And with that, balances the increased performance with increased performance in LSPI prevention, aeration, and turbo deposit prevention. And then also the one key thing as we go through this today, there is a realization the new specification will be a challenge to the additive companies and the oil companies in terms of developing a balanced formulation to meet all these new requirements while retaining the robustness in the current standard test requirements. The goal is, or the hope is this at least allows folks to have a precursor or be able to use this as a stepping stone for the upcoming GF6 specification. In terms of the dexos1 specification, we're addressing fuel economy in three different ways. The one thing is we're package protecting for ultra-low viscosity oils, for example, the XW16 oils. Even though our product side is does not have anything in the upcoming portfolio regarding XW16 oils, we think it's a good idea to go through and package protect for that. In addition to that, we also include a vehicle fuel economy performance test requirement, and that's something new. I'll get into that in a little bit, and that's in addition to the sequence 6D/E. And the third point is the goal is to generate more robust 0W20 and 5W30 formulations for the turbo applications. Those turbocharged DI small displacement engines, basically, I think we're not just the only OEM that has challenges with these engines. Everyone knows about LSPI, and everybody knows about turbo deposits. So as we move forward with more of these engines in our portfolio, these two areas are going to play a huge role in terms of where engine formulations go in the future. First thing I want to touch on is low viscosity and fuel economy. I think most people know that decreasing viscosity increases fuel economy. There's been several papers written on this, several presentations presented about the same topic. However, the one thing to emphasize is if an engine is not designed for a lower high temperature viscosity, then an increase in fuel economy will not be likely. That's something to emphasize. This is a prime example here. This is based on the US FTP cycle, FFE, and the US combined. And what I'm trying to demonstrate here is a 0W20 oil, 0W30 oil, both with equivalent chemistries. And this is percent fuel economy increase over baseline of a 5W30 And this was actually run on a 3.6 liter engine in an Impala. And what this demonstrates is this Impala, or this 3.6 liter engine, is actually designed for a 5W30 oil. And as you can see here, if you jump down to an XW20 oil, you actually see a hit in fuel economy, where, you know, obviously you're going to get a bump up because of the zero with the cold effect. But your XW30, that's where that engine's happy in terms of operating. So that's a prime example on why it's very key that the viscosity grade matches up with the given engine design. And it's not just a broad brush philosophy of if you just drop your high temperature viscosity, you'll automatically get increased fuel economy. That's not true at all. It's all in the engine design and how that design works. Another example of this, common knowledge that ultra-low viscosity oils are an enabler to the fuel economy increase. Absolutely. In terms of XW16s, even lower, getting into the XW8s, some companies are. Absolutely, they're an enabler to fuel economy. But once again, it's all in the engine architecture and how those engines are designed, how the bearing systems are designed. You're going to get certain appetites for certain engines. And again, it just goes back to the design being key here. This was actually taken from a 2013 SAE paper called an Experimental Evaluation of the Impact of Ultra-Low Viscosity Engine Oils on Fuel Economy and CO2 Emissions. This was from Massimo Manni and Salvatore Florio from E&I SPA, and again, published in 2013. And what they did was they took two vehicles that had two completely different architectures, different transmissions. They both had four-cylinder engines, but obviously they were two different designs, especially when you can look at the engine displacement here in cubic centimeters. So and what they ended up doing is running some fuel economy testing with these and experimented with different oils. The recommended engine oil for vehicle 1 was a 5W20. For vehicle 2, it was a 5W30. And what they proceeded to do was they had four oils here. R was considered the reference, which was a 5W30. And then they had a 0W20, a 0W16, and what they called back then a 0WX. And if you look at the viscometrics here, HTHS, I mean, 0WX is a 2.0. Your 0W16 is the 2.3, 2.6, and then 2.9 for the 20 and 30 weight. In terms of vehicle 1, and this is a hard chart to, when you first glance at it, it's very deceiving. This is actually percent fuel consumption. So negative is actually good for fuel economy, so just bear that in mind when you see these charts. But as you can see here, you know, it actually, as you go down in viscosity, your fuel economy gets worse with vehicle 1. However, with vehicle 2, it's the opposite. As you can see there, the engine takes to the ultra-low viscosity oils quite nicely, as you see a trend downward, which is good for this chart for fuel economy. So again, it gets back to reiterating the point of the importance of the engine design and the architecture, and whether or not an ultra-low viscosity oil will work for a given vehicle in terms of increased fuel economy. This gives some conclusions here. The study concludes vehicle 2 favored lower viscosity oils over vehicle 1. The architectures, again, they have to be designed around the desired viscosity grade for optimal fuel consumption for that particular architecture. Right now, our architectures are currently designed around XW30 and XW20 oils. As smaller displacement engines are considered for fuel economy enablers, and there's interest around XW16, those oils will be strongly considered. And because of that, we wanted to be proactive in the specification and at the very least include XW16s in our dexos1 specification. That way it's there, it's ready. If our product guys want to pursue that in a future engine architecture, then we can have those formulations ready to go. Another area for addressing fuel economy was actually adding an additional test to the dexos1 specification, and that was actually incorporating a vehicle fuel economy test. GM is the first North America OEM to go through and incorporate such a test for its global aftermarket and factory fill specification. It's a common practice within Europe and the European-based OEMs, so this isn't a foreign concept over there. As a matter of fact, that was a concept that we decided to adopt based on the learnings over there in Europe. We believe it provides insight for fuel economy performance, and we can scope it so it's in a range of vehicles. That way we get a better understanding of fuel economy across a good cross-section of our portfolio, because within GM our portfolio is so diverse. You have anything from V8 trucks all the way down to like a 1.4 liter Sonic. So with that, our final fuel economy test will actually include a handful of vehicle applications that will represent GM's portfolio. With that, it'll include a V8 truck, it'll include a V6 Impala, and then a 1.4 liter Cruise. It addresses the issue of engine vehicle applications having different appetites and formulations, and that is nothing new to anyone. I think that's been emphasized in the past few years, that every vehicle application and engine architecture is going to have a different appetite. Initial vehicle fuel economy test only evaluates fresh oils. So the one that we have in our specification right now that we launched with, we're actually using this little, I'll get into it a little bit, but we're actually using a 1.4 liter Astra, which is our sister vehicle to the 1.4 liter Cruise. And that's being run over at ISP. And our launch was just running this car on chassis dyno, and only looking at fresh oil, no aging with this test right now. What the goal will be is to incorporate an aged oil evaluation in the future, primarily with the Silverado and the V6 Impala. That should be coming out later on this year. This kind of gives you an example of how we approach this. So basically, there's 3 oils here, very similar viscometrics, obviously a 0W20, 3 different additive packages. And again, for specification, and for this particular subset of a larger oil matrix, we used 2014 1.4 liter Opel Astra. We actually use the NEDC over at ISP, and that's what the European OEMs use today for their vehicle fuel economy work for their individual oil specifications. What we do is we run that, and we do an average of 4 runs per oil. And as you can see there, that's actually the actual Astra on the chassis dyno over there. So with that, oils 1 and 3 are relatively similar, but oil 2, there is something unique with the additive chemistry, and I'm not going to disclose what that is, but it gives us a more favorable number in terms of fuel economy. And what this is based off of is a 5W30 baseline. What we ended up incorporating is a different reference oil for the specification. So instead of using the typical higher viscosity reference oil that you would see in the Sequence 6D, we actually thought it was more realistic, being that most architectures are at 5W30 today, to use that as a baseline. So it's a special oil that's formulated where it doesn't present a VM effect, and we use that as our baseline. So basically, that chart illustrates that oil formulation differentiation is present in fuel consumption, primarily of the Astra, based on the NEDC cycle. And it concludes that oil formulation does play a role in optimizing fuel economy. Second generation dexos1 specification challenges formulators to optimize the additive chemistry within a given viscosity grade to ensure we've got the best fuel economy moving forward, and obviously with balance for the rest of the performance of the specification. This will be a big enabler for us for certifying vehicles across the globe. Everyone is getting more and more strict on their fuel economy and emissions guidelines. And we think that that results in engine oils which are a part of the fuel economy solution. We think that's a big part of the solution moving forward along with the new architectures. In terms of robustness, this is extremely important for GM in terms of moving forward with fuel economy, getting back to increasing the portfolio with the turbocharged small displacement DI engines. They're playing a big part for us moving forward with meeting the fuel economy requirements. However, like most OEMs, they present challenges, and that's along the lines of turbo deposit and LSPI. And we're finding engine oil formulations play a major role in both of these. So we've developed 2 engine tests for the second generation specification that addresses both of those concerns. I'll get into those. That's the LSPI and the turbo deposit test. For the turbo deposit test, we actually had a vehicle field issue where we found a particular drive cycle posed an issue with one of our applications with significant turbo deposit formation, so much so that we would lose turbo boost. So what we did was we took this drive cycle and we created a dyno test based on that to simulate the conditions. And what that boils down to, it's basically like a start-stop test. It's not severe at all. The one thing that we noticed with this test, it does not degrade the base oil whatsoever, which was a big surprise to us. Everyone's always has that question, what is the deposit itself? There's always been theories around base oil and if that is a cause. And at least with this particular drive cycle, base oil stays intact. And that's based on GC analysis as well as evaluating viscosity change. And what we use for a limit, it's based on temperature increase in the turbo housing. What we found was we correlated temperature increase with the amount of turbo deposits formed and at what point in time we start to lose boost. So we did a lot of work behind that, and that helped streamline the test a little bit, but it's a very long test regardless. This is some examples of turbo deposit, in case you have not seen that before. That's what we're talking about. And just to give you a 101, some basics in terms of in terms of the oil flow into the turbo. What you're looking at here, I just want to kind of walk through oil flow. But what you do is you start from the engine oil gallery, and you go through the feed tube, into the turbo, out of the turbo, and then into the drain tube that goes back into the engine. The whole function of an oil for the turbo is cooling. And that's why many of the turbo manufacturers require 5W30, just based on the turbo designs. They're not quite there yet in terms of using a lower viscosity oil. I know some of them are working on initiatives to get there, but right now 5W30 is the oil of choice. And again, it's based on that function where the oil has to act as a cooling mechanism to the turbo. What ends up happening when you get turbo deposit, You're going to form it here within the turbo, and you're also going to form it right here in the drain. You'll get it in the drain tube. Sometimes you'll actually get it in the feed tube too. And the one thing that we found was different additive chemistries will form deposits in different areas of the turbo system. And it's consistent, so you can repeat it. So it's not random. It's very, very much closely tied to the additive chemistry. This is just a picture of our GM turbo deposit test stand. We've got several test stands over at Intertech Automotive. And this depicts our test cycle on kind of a high level. So basically it's a flush and run, double flush and run test. We use 3 liters of oil. We do oil samples every 100 hours. No oil cooling and no turbo cooling. But as you can see here, it's not a very aggressive test cycle. So what it is, you got a 30-second idle time. You ramp it up to 3,000 RPM, 80 kPa map. You hold it there for 6.5 minutes. And then after that, you do a slow ramp down. And then you have the engine off at this point. You do just a soak for 7.5 minutes. And then you repeat. This is a very difficult chart. I apologize. I couldn't get it dark enough. But the key thing here, these different colored dots, the yellow, the red, and the blue, those are 3 different oils, 3 different additive chemistries, same viscosity grade. And what you'll see here is they break around the same, this is kind of like a time scale. They break around the same time. However, where they deviate is after they break. And there'll be some publications coming out either later on this year or early next year in regards to this phenomena. But what we're finding out is there's one primary antioxidant that's very common in all these additive chemistries. That's usually the first to go, and it goes at the same time. And then after that, depending on how robust the additive chemistry is, that's where you actually see your differentiation in your formulation. And that's correlated to the amount of deposit that you form within the turbo. And again, there'll be some upcoming papers coming up to get into the details of that full study. Jumping into pre-ignition, just to reiterate what Hirano-san went over yesterday, he did a very good overview of LSPI. Basically, what is it? It's an abnormal combustion event at low engine speeds at high loads. And basically how it's characterized, it leads into high cylinder pressure and heavy knock. And it's often in multiple cycles in length. Usually oscillates between pre-ignition and spark ignition. And this gives you an indication of what a typical pre-ignition event is. So you'll have the normal, it'll be humming along, and then all of a sudden you get a blip. You'll get another blip. So these spikes here represent the pre-ignition event, and then you're back down where you need to be. So the one thing that we always get asked by many oil companies and additive companies is, okay, so what? How does this harm your engine? You can get a lot of harm from this. At the minimum, it's a customer dissatisfier because they hear a noise along the lines of a hammering noise. That's at a minimum, so it's a customer dissatisfier. You're driving in the vehicle, you hear this hammering noise, and you're taking it in wondering what's going on with my engine. Or what's going on with my vehicle, because many customers don't even understand that it's their engine. The second point, if you get a repetitive mid-load, a number of these events, or a single high-load event, you can cause significant damage in the engine. Some examples are spark plugs. If you can see there, we actually busted the tip off the spark plug. Piston ring lands, that that usually, between the piston ringlands and connecting rods, that's usually catastrophic on the engine. This isn't a very good picture, but it shows part of the land basically blown away from the combustion event. So this is a big deal for us. So what we ended up doing is we developed an LSPI test for the second generation dexos1 specification. We did this because it was demonstrated through the P3 consortium, which was held at Southwest Research, that engine oil additive chemistry plays a role in LSPI. It's not the sole reason. I call it there's three primary areas, or actually four primary areas that impact LSPI. It's engine oil, it's fuel, engine calibration, and engine hardware design. So all four of those play a role in LSPI. Obviously, with engine hardware design, we try to do our best to mitigate. However, we can't resolve LSPI altogether. That's where we need help from the other areas. We'll calibrate as well, but we start to lose performance. And again, that's where we need assistance, especially with the engine oil. Fuel, as everyone knows, is a bit more difficult to control. There's general guidelines that folks follow, but that's a hard one to control, especially on a global basis. So what we call low-hanging fruit for us as OEMs is looking to the engine oil to help give us that additional improvement. So with that, we developed our LSPI engine dyno test that differentiates oils. Limits have been captured, and it's to ensure that oils are less likely to aggravate the situation, to aggravate LSPI. We know it's not going to solve LSPI in and of itself, but we do not want to make the problem worse. So this just goes through briefly the conditions of the test. We've got 4 stages: an oil conditioning stage, engine conditioning stage, cool down, and combustion. We use a 2-liter turbocharged LHU. This gets into some of the parameters, and the one thing to show here that is different than Toyota's test is that we do run a little bit higher of a coolant out temperature. They run around 60, we run at 95 degrees C. We know that there's sensitivity differences there where our test isn't going to be as sensitive, but overall we can still rank the oils in the same manner. This just gives you a picture. This is an LSPI event right here in a given trace. And this is just a blow up of that LSPI event to give you an idea. Just a quick demonstration, just to give you an idea. These are 2 oils, 5W30. They've got 2 different base oils, I'll acknowledge that, and 2 different additive packages. And what this shows is oil 1 has more pre-ignition events than oil 2. The averages were based on 10 runs for each oil. And basically how the specification is laid out, it sounds complicated, but it really isn't. We require oils to have at least 3 out of the 5 consecutive runs with no pre-ignition events. And then out of those 5 consecutive runs, no more than 2 of those runs can have peak pressure events per run. And peak pressure for us, we've got defined within the specification. So in summary, we have introduced our 2nd generation dexos1 engine oil specification to help address fuel economy indirectly and directly. This new specification focuses on providing GM support in meeting the more rigid fuel economy requirements. We're package protecting for XW16 oils. We're enhancing our fuel economy requirements, and we're increasing robustness in areas that are critical to our small displacement turbocharged DI engines. Again, this will be a challenge for the industry to provide balanced formulations to meet these requirements. And this, again, to emphasize, this new specification may serve as a learning opportunity to allow formulators time to develop formulations for the upcoming ILSAC GF6 specification. And that's it. Thank you.